Okay, so the presentation is based on the paper which we published few years ago, and actually, as it is said, it is going to talk about experimental evidences of one of the most puzzling properties or lack of properties of gallium manganese arsenide, the canonical dilute ferromagnetic semiconductors. That is the lack of the observation of false fault anisotropy switching in this material. So before we proceed to the subject, let me just say 2 words about the origin of ferromagnetism in this material, because this is very important to understand why the feature I'm going to talk about is so important. So in order to understand how the coupling or the ferromagnetism is possible in this material, we can start from treating our mixed material as 2 independent worlds. So one is the semiconductor basis, which is p-type. In this case, this p-type gallium arsenide, and the holes are actually brought about by manganese atoms which are there. If these 2 worlds are independent, if there is no coupling between them, and then the manganese spins are basically uncoupled, or there is a weak antiferromagnetic superexchange between them, and these 2 worlds simply live on their own. However, when the coupling is introduced, then actually it turns out that it pays for the system to organize, to polarize all these manganese atoms, so they create non-zero magnetization, and in the presence of this exchange field due to this magnetization, the valence band of hole splits, and this is the redistribution of the carriers, which actually lowers the energy of the carriers, which provides additional energy gain. So then the entropy penalty imposed by the ordered manganese atoms ions can be compensated. So the highest temperature in which this energy gain in holes overcompensate the penalty of entropy by the manganese atoms is the Curie temperature for this system. And actually, this is the interaction between the holes and manganese, which is responsible for the very rich magnetic properties of this system. So gallium manganese arsenide is grown basically exclusive. I mean, there are some other cases, but the main source of these materials are epilayers grown by MB techniques. These are grown on gallium arsenide, and now depending on the difference between lattice parameters, we can obtain materials usually in compressive strain, but if we use some stressing layer here, we can obtain tensile strain case. And the major physics I'm going to talk about actually takes place in the top of the valence band, and this is the splitting of the valence bands into heavy hole, light holes, which actually is responsible for the magnetic properties and magnetic anisotropy most predominantly. And for example, the phase diagram is quite rich because, let's say, for the same manganese concentration and the same epitaxial strain, both cases of easy z-axis magnetization, which is perpendicular magnetization, and easy plane magnetization can be realized in exactly the same sample, depending either on the temperature or on the hole density. So, for example, we can switch from easy plane to perpendicular case by changing the hole concentration, and this actually has been shown that it is possible, and realization of this and the communication in nature in the paper, and that was published in Nature 2008. Just for the, say, historical record, because for many people gallium manganese arsenide grown in the compressive strain case is regarded as in-plane material. So this is compressively strained gallium manganese arsenide, and in this case perpendicular magnetic anisotropy is clearly observed. So the magnetization curve measured in this configuration with the magnetic field applied perpendicular to the layer has easy axis character, and for the same sample, the same conditions, magnetization measured in plane has got a slopey character indicating the hard axis orientation. So the theory developed for this material proved to be very rich in magnetic properties, and for example, one of the key finding of this theory was that the lowering to D2D symmetry should impose fourfold, or you may say biaxial, in-plane magnetic anisotropy, and this magnetic anisotropy should switch between either 100 easy direction to 110 easy, and then 110 easy, depending both of the hole concentration. So these are the calculations done as a function of the hole concentration, but the same switching can be observed as a function of temperature and as a function of manganese concentration. Basically, this is due to the fact that what is important here is the ratio between exchange splitting and Fermi energy. So all these things depend on these parameters in this material. So that's why such a rich possibilities are expected. However, the experiment, and there are many experiments done, indicated that exclusively 100 orientation, the easy orientation for this cubic or biaxial turn, has been observed. So in the language that is normally used to describe magnetostatics of this material, it is the result is that the cubic, so-called cubic, this fourfold in-plane symmetry, that the cubic term is positive, as I said, exclusively. However, perhaps the main obstacle to observe this rich behavior is the presence of additional strong uniaxial in-plane magnetic anisotropy between 110 and minus 110 direction in this system. So the total magnetostatic expression for this material looks like this, and well, in order to find switching of cubic anisotropy constant, a relevant experiment has to be performed. The authors of this paper, Gittl and Kowersker, said that perhaps it will be difficult to see because we need sample of exceptional homogeneity, simply due to the fact that the broadening of the bands may smear off these transitions. So we initiated our search by selecting the samples of, for us, the best possible homogeneity. And for example, we found 3 of them, and this report is based on the results obtained for these samples. And it was quite exceptional that on the whole wafer, let's say 2 centimeter, 2 by 2 centimeter large piece, the difference between Curie temperature between different pieces was smaller than 1.5%. That was truly exceptional. Then the first experiments that we performed was FMR, and the results of our measurements done at 6 Kelvin and 50 Kelvin are summarized here, and the experimental points are these open circles. And it turned out to be possible to reproduce this experimental dependency very well, and to do this we needed one uniaxial term. So this is the one in this expression, and this red dots, and a cubic term, and the cubic term is this one. So at 6 Kelvin, this cubic term looked like this. At 50 Kelvin, it looked like that. So there is clear 45-degree rotation between these two cubic components, and this actually means that the cubic anisotropy constant has changed sign. This 45 rotation means the change of sign. However, what is very important here, please note of the number that the uniaxial anisotropy constant is an order of magnitude stronger than the cubic term. So as you see, someone has to believe, really has to believe that the fitting was done okay, and that this rotation really took place. Nevertheless, one could say, yes, we see the change of the sign of the cubic anisotropy constants. Cubic anisotropy indeed oscillates, so somehow this prediction has been confirmed, and to a large extent I could stop my presentation here because it looks like the job is done. However, we regarded this this finding as not really conclusive, so we wanted to find a direct magnetization measurements evidence that indeed this change, such a change took place. And the main challenge is that the cubic anisotropy constant is, as I said, an order of magnitude smaller than the uniaxial one, so the experiment has to be performed in such a way that we can see this change. So we, as I said, we are hunting the change of the behavior along 100 orientation, and from FMR we knew that there should be a difference between 5 Kelvin and 50 Kelvin. So now I'm just showing you the results of direct squid magnetization measurements, and we've got open points are from 5 Kelvin and full symbols are from 50 Kelvin, and measurement along this 100 orientation, the one which is of the prime interest for us, actually shows no difference whatsoever. So the behavior of this magnetization is directly controlled by the uniaxial magnetic anisotropy, and there is very little seen here. So let's go to 110 orientation, to the orientation. This is the orientation into which cubic anisotropy switch. But again, there is no difference. This is simply, I mean, both temperatures, open and closed symbols, show basically there is no big difference, well, except of just the width of the coercive field, but that is too little to say anything about magnetic anisotropy. Okay, so if this orientation didn't show us anything, so we switch to 110 orientation, and now there is a change. So in these two temperatures we see two kind of characters of this magnetization curve. So there is a concave curvature here and convex curvature over there. So at high temperature we've got convex, and at low temperature we've got concave curvature. The question, is it the thing that what we really wanted, or is it something else? So in order to do this, we have to come back a little bit to the very simple mathematics, and we have to solve this equation, which is not particularly difficult. We can introduce relative units of projection of the magnetization along 110 orientation. This is exactly what we measure in squid magnetometry. We apply magnetic field along this orientation, and we look on the value of the magnetic moment, the projection of the magnetic moment on this orientation. So somehow we should get dependence like that, but to get the form of this dependency, we should solve this equation, and this is third order polynomial, and actually the general solution for such a case is very complicated, and it's not really instructive, and there is zero educational value. However, what we can do, we can actually rotate by 90 degrees our coordinates, and now we can observe that this is just this expression before going into the lengthy calculations of solving this third order polynomial actually relates us magnetic field with this value of m, the projection of m, and actually it has very simple form. There is a linear term and a cubic term. So this is simple to analyze, but you have to plot the results in slightly different way. So let's start from the uniaxial behavior. So let's forget about the cubic anisotropy. So these terms go away. And indeed, what we get is a typical textbook expression for uniaxial magnetic anisotropy. So the magnetization should go this way, because this is linear relationship between H and M. So M is here, H is over there. So it's a linear increase. Of course, mathematics says it should go infinitely, but the physics says m cannot be greater than 1. So we should get something like that. This is not particularly important how it goes. There is very important factor here, that the slope of this slope is set by the value of the uniaxial anisotropy. So this is just m over ku divided by 2. Okay, let's move further. And now let's say that there is cubic anisotropy, but it's weak. I mean, it's weak in that sense that we are measuring only weak magnetic fields for which m is, let's say, closer to 0 than to 1. Then we can still forget about this cubic term, because that is definitely much smaller than that. I mean, you have to keep in mind that m dash is always smaller than 1. So cubic, so number smaller than 1 to third power is definitely smaller than this m dash. So we are still having linear relationship, but with a different slope. And this time, please note, the slope is just given by the difference between this cubic anisotropy constant. So that line, as you see, starts at different angle, different slope, depending on the sign of the cubic anisotropy. So indeed, sign of the cubic anisotropy changes something. It modifies the magnetic response, but only at this particular orientation, what I showed experimentally. And now when we just allow the and the value of a cubic constant, and if you just get the so to get the full expression, we are switching on this term, and this term means that for positive value of Kc, we've got positive curvature, so we should go like that, and for the negative value, we certainly should go like that. So now I will just rotate this to the normal experimental unit, and we find something what resembles very strongly our experimental findings, which look like that. So the conclusion of this part, that indeed this change of the character of the hard axis magnetization from convex to concave indeed reflects the change of the sign of the cubic anisotropy. And now we can, for example, compare the results for a few temperatures. So we plot here. Now we are now working in the standard coordinates. So we've got magnetic field on x-axis, and we've got reduced magnetization on the y-axis. So when we are at 5 Kelvin, these are the red points. So we've got concave curvature and with this initial slope. Then we go to 50 Kelvin, blue points, and this is this convex curvature, and this is the initial slope. Then at 110 Kelvin, we've got again concave curvature. And this is very interesting. At 80 Kelvin, looks the curve goes straight nearly to the maximum values of n equal 1. So obviously, this linear relationship at 80K says that at this temperature, cubic constant should be nearly 0 because we are having only this linear relationship. Okay. So in analysis of magnetization data, what is important, we just calculate the slope, this initial straight line. From this slope, we are getting the difference between these two parameters, and then we adding only the curvature, so we can get the value of Kc, and we've got Ku from that difference, which defines this initial slope. So actually, you don't need any parametrical fitting of experimental curves. You just use this. What you need is just a ruler and a pocket calculator to calculate all the numbers. So the summary of our finding, because we did the measurements for 3 samples, is the following. That let me start from this less interesting, the uniaxial anisotropy constant as a function of temperature. It goes like this, and this full points are established from magnetization curves. The points established from FMR are marked with open symbols, and as you see, they coincides very nicely with those established from magnetization. And now when we turn to blue points, which is the cubic anisotropy, and we see that the curve is quite complicated, and it's very funny, but we've got not one, but we've got 2 switching. So we start from positive value, then we move to negative values, and then we are in positive values again. Very similar situation. So this is a function of temperature. When we study it as a function of hole concentration, this can easily be done by annealing. This low temperature annealing is known to promote, to increase hole concentration. So we can sequentially anneal one sample and measure and measure and measure. And what we established, so for example, as a function of annealing, we see that the Curie temperature goes up, and this is one of the indication that the hole concentrations was indeed going up. And our experimental points, this is for Kc, looks like that. So again, we are, let's say, starting. So this is a ground sample for positive cubic anisotropy, then we switch to negative, and then for the maximum annealed sample, we go to negative again. So there is a theory which took into account broadening of bands and so on. And the theory, whatever we are doing, gives only one change of the cubic anisotropy. That there is no place in this in the theory to have 2 transitions. And to have these 2 transitions, we have to step back a little bit from the picture of an ideal system. Let me just start from the finding that on this graph we collect the Curie temperature taken from many papers, about 75 papers, plotted as a function of the thickness of the layer. And there has been a general trend seen that the Curie temperature was getting higher and higher as the layer thickness was getting thinner and thinner. However, let's say below some 15 nanometers, something strange happened because the Curie temperature was going down. And that wasn't generally understood why, and we provided in different studies some of these evidences, and actually the evidences are the following, that gallium arsenide as a material has got a lot of surface states, and these surface states are predominantly donors, so they reduce the number of holes at the interface. On the other hand, this material is grown usually on low temperature gallium arsenide buffer, which is N-type material. So we've got drainage of holes out of the material on the both surfaces, with the buffer and with the free surface. So as long as the layer is thick, then these effects can be disregarded, and Curie temperature, for example, Curie temperature is here. So Curie temperature is quite high. But now, as we thin the layer, and this is the result of experiment. This is one sample when we thin in so many steps, the Curie temperature is going down. And the only way to understand it is that as the layer is getting thinner and thinner and thinner, more and more holes are taken away from this system. So, so this is the general expression for the Curie temperature in this material, and it is actually, so here stays the spin susceptibility of holes, and actually that's why with the lowering of the hole concentration, TC goes down. So these things are very much related to our studies, since our layer, those which I showed you, are also very thin. So also they are depleted of holes at the free surface. They are depleted of holes at near the low temperature gallium arsenide buffer. And as the result of this, the ferromagnetic coupling is maintained only in the center, when the hole concentration is high enough to support ferromagnetic coupling. Otherwise, on both ends, so near the surface, there is no long-range ferromagnetic coupling. The coupling is maintained only in short distances, so we are having superparamagnetic-like properties. And these superparamagnetic-like properties have been, were proved to stay in this material. And for example, it has been shown by electrical gating that we can change the relative concentration between this superparamagnetic and ferromagnetic component, and also the change of the Curie temperature was observed. Yeah. So another confirmation of this superparamagnetism comes from scanning tunneling microscopy, when actually the surface of gallium manganese arsenide can be visualized with atomic precision. In this very nice representation, each dot is an atom, and the colors actually corresponds to the density of states. So we've got low density of states here and large density of states over there, and then you see that at the surface, so at the surface of the material, the landscape is very, very complicated. So the ferromagnetic coupling is maintained only in this red or brown regions, when the whole density is high enough to support ferromagnetic coupling. There is no ferromagnetic coupling whatsoever in these places, because there are simply no holes. But actually what you see, many of these, let's say, hills are separated from the other. So if there is a ferromagnetic coupling, it's at the best only percolation like, and there is no way of assigning a global global coupling. So this superparamagnetic contribution actually gives another concave components to our magnetization, and in our understanding, this is this superparamagnetic concave character that at low temperatures that actually pushes the appearances as the Curie constant is getting positive. So when we compensate for this, effect, our points are really going down to negative values as the theory actually predicts. So this drives me to a summary. As a summary, I would say maybe why this not has been seen before, why we were only the first. And in our view, these are two things. First of all, at some point, many researchers were just interested in the best possible materials with the highest possible Curie temperature. So even the freshly grown samples were immediately annealed. And so they were actually going to this regime where the cubic constant was indeed positive. If anyone was performing measurements at very, very low temperatures, then of course this super paramagnetic component was giving this concave curvature, obscuring the change of the cubic anisotropy to the negative values. Actually very few people were interested in this middle temperature or middle whole concentration regimes where the cubic negative values of cubic anisotropy were possible to see. So to some extent we were double lucky. First of all, we have very homogeneous materials, and secondly we perform wide-ranging studies, and then we are able to find these critical regions where this effect was able to be observed. So this is the end of my presentation.